Our first talk by Artjoms will be on an application of polynomial functors or containers to array programming. So go ahead, Artyom.
All right, thanks. As you correctly said, so this is going to be my journey through trying to formalize arrays in independent type contexts using containers, discovering a new container operation that seemingly is unknown to people and in literature, discovering that using this operation you can have an interesting array hierarchy of types, and basically looking at a practical application of this thing. So when I say formalizing arrays, what I mean is this. So I'm aiming for, well, first of all, rank polymorphism. That's the bread and butter of array programming. So the ability to be able to define functions that operate on arrays of any rank and shape, right? Then I also insist on checking bounds statically, so that indexing errors, out of bound indexing is impossible at runtime. And I want to be able to represent any operator from the APL programming language, because that's, well, the essence of the array programming, right? And extensibility is nice, but that's optional. So it is important to mention that if we seriously take these conditions these criteria that I've described, then we inevitably have to use dependent types, because, well, if you want to statically track the shapes of the arrays, it's the easiest way to do it is in the type. And if you want to support operations like take and drop or many other APL operators, then inevitably you'll find yourself in a situation that the shape of the result of the operation depends on the value of the argument. Therefore, dependent type is essential here. And here's the first approach that basically fits all the criteria. That's a pre-container approach that I started from. So basically what we do here is we model the array as a function from some index space to values, and arrays keep the elements of type X. And here's a function that models, well, that gives a value to the array. And just to be sure, we're talking about hyperrectangular, homogeneous, multidimensional arrays. So it means that the shape of the array is fully defined by a vector of natural numbers, which basically explains the length of every axis in d dimensions, right? And then what is the indexing? What is the index space of a given shape? Well, the index space of a given shape is basically also a tuple of natural numbers where each element is bound by the corresponding element of the shape. So the index must be component-wise less than all the elements of the shape. But it's important to mention that's going to appear later, that the structure of the shape and the structure of the index always match in this model. Okay. So using this thing, basically you can do a lot of things. And for simple cases, like you see on this screen, you don't even have to provide many proofs, right? So if from the way the types are constructed, when you write, for example, operations on matrices like transpose or matrix multiply, as you get down to the individual index components, and you carefully reshuffle them around, then the type checker it can see that basically all the indexing is correct, and you don't have to do any kind of actually proofs. If you really work on rank polymorphic operators, then surely you might find yourself defining some properties. But in simple cases, it works out very nicely and automatically. And then how do we get here from here to containerization? First, let's remind ourselves a bit what containers are. It is a lot of things, but for the purpose of this work, for this paper and for this talk, as the name suggests, really, it's a collection of indexed things, right? And in order to define a container, you have to choose a type for the shape, and you have to choose a position, which is a shape-indexed family of types, right? And then the interpretation of a container, so basically the operation that gives you access to the actual elements, is given by this function. So to interpret container with element type X, it means that we just create a dependent pair where the first element is the shape and the second element is a function from the positions of that shape to X. Okay. So in that sense, for example, list is an instance of a container. So list is defined by a container nad_fin. And if you expand the interpretation, then you'll see that basically it says that, well, list can be modeled by a dependent pair where the shape is the natural number, so just the length of the list, and then the positions are functions from fin to X. So really, the nice point for me is that containers give you the most they never talk about the way your data structure is organized, right? So you just have an interface in the form of a function, and the function says, well, okay, you have indexable thing, and I'm not going to explain what is the internal structure. So if you think about a compiler, it means that, well, from this representation, you can implement your actual data storage in any which way you like. You know, the interface doesn't care. Okay, so array is obviously a container, and let me explain how would it look like in the containerized representation. So first, let's recall that vector can be modeled by the function fin to X, right? That was just on the previous screen, and the indexing can be modeled like this. So it is also a vector of d elements, but where each element is fin of the corresponding shape component, right? And in that case, array is just a type constructor that takes the rank, the shape, and a function from indices to values. Okay, so that's what we start from. Then we can uncurry first two arguments and notice that this function here looks suspiciously like a function here, right? So we can rewrite already the array type as an interpretation of the container, where the first element is going to be a sigma, well, the vector, in essence, the vector of natural numbers, and the second one is going to be the positions are going to be the IX type written with fins. Then we can notice that the sigma is also a container itself, right? So as I was showing on the slide before, and from looking further at this, we can notice that this operation suspiciously looks like a result of some operation on the containers, right? And then we try to think carefully about how the general operation on the containers could look like in order to produce such a result, and we came up with this formulation, right? So we call this diamond. It, I'm not sure why. Well, is it a good name or not? Doesn't mean much. So what we do in order to compute the result of two containers, we say, okay, so we interpret the first container with the shape of the second container, and then the positions of this operation are going to be given by a product of D's, right? And then we have B many D's, right? So we're creating a dependent function that basically puts D's together. And in that case, the array can be rewritten as a NatFin diamond NatFin interpreted with X. And somehow, if you think about rectangular arrays, some sort of vectors thing is happening there. So that is reassuring. Then the operation itself in isolation turns out to be rather interesting. Well, first of all, it looks like a weird operation. It's not associative. It's not functorial on both arguments. It's only functorial on the right. People never tried this operation before, and it's not clear what exactly it's doing. And I think the satisfying explanation on what it may be doing is by looking at its relation to an operation on container that is known as a tensor product. And the tensor product is defined rather straightforwardly. So you take, if you want to compute a tensor product of two containers, then you pair up the shapes, and the positions are also paired up. And if you think about a classical tensor product, then really that's exactly what is happening, right? So you conceptually you choose the shape of both containers up front, so this A pair AC, and then at every position of the container AB you insert the containers DC where C has been chosen beforehand. So it's kind of this homogeneous nesting of things. And then the next question you might ask, what happens if you want to compute an n-fold tensor product of container CD? And how do you even define this operation? Well, how do you give the boundaries to this tensor product? Well, you can surely choose to give a natural number and then recursively unfold the multiplication, but you can also choose to set the boundaries of this tensor product by using yet another container, and that's really what is happening in this diamond operation. So basically, we choose a container AB, and then we say, okay, just plug the container CD without interpreting it at all the positions of AB, right? So just plug the container CD and then fold the tensor product, right? So really, one way of understanding this diamond operation is it's a generalized tensor product where the left-hand side is this counting container or boundary container. And yeah, the funny analogy that one can observe with this diamond operation, that it has a similar behavior to tensor product when we compare to container product. So in the container product, you compute also you pair the shapes, but the positions are so you compute a co-product of the positions. But if you go to tensor product, then you replace this plus by times, right? And then this diamond operation does a very similar thing to the container composition. So in a way, you replace a sigma with a pi, which, again, if you think about it for some time, then it kind of makes sense. I mean, there's this tensor nature of this diamond operation. Now, the interesting thing about this diamond is that as it's closed on containers, you can iterate it. And you can iterate it in two different ways. You can associate, well, you can define this operation to be associative on the left and on the right. And you can start with a unit container, so it's a container of one shape and one position. And then, well, you can iterate. You can keep multiplying on the left or on the right. And as the operation itself is not associative, you're going to get different results. And it is instructional to look at the third application of, well, either AL or AR. And what happens here is that if we are right associative, then by multiplying kind of on the left side, keeping multiplying on the left, we enrich the structure of this boundary container. So the boundary container turns into inhomogeneously nested n-dimensional array. So in the third instance, it is a two-dimensional. In the fourth instance, it's going to be three-dimensional, and so forth. So it's a vector of vectors as many times as you multiply this, and the rest is the same. So the indices are going to be exactly the same form as here, but they're going to be bound by corresponding elements. Right? So you can create arrays of these weird shapes. And if you choose to make this operation left associative, then what happens is that the array of level 2, well, array of level n becomes the shape of the array of level n plus 1, and that's easier at least to understand this from this table. So we start with level 0, which is which shape is just a unit, and well, in positions, the arrays at level 0 are just zero-dimensional array, typically called scalars in the array theories, and they only store one element always. Then level 1 arrays are they have shape level 0 of natural numbers, so just one natural numbers, and well, they keep so many x's, right? So they keep a vector of elements. These are just vectors, right? Level 2 arrays, that's the multidimensional arrays as we know them. Their shape is characterized by level 1 arrays. So the vector of natural numbers, and then you can carry on. So for example, level 3 arrays are arrays which shape is characterized by the multidimensional arrays. So the shape itself and the index, the corresponding index into such an array is going to be multidimensional. So all we do here is we enrich the structure of shapes and indices. Now, it is important to mention that here we're not creating a conceptually new data structure, because everything above level 1, all the arrays of level higher than 1 can be mapped into vectors, right? But that's already a well-known thing. So I mean, if you have a container of finite number of elements, and you can order your indices, then well, you can surely linearize the content of your container into a sequence. So then the question is, well, okay, but if it is the case, then why do you want to have multidimensional arrays at all, yet these crazy multi-dimensional arrays? And to answer this, let me give you a brief demo. So I mean, this is the hierarchy that I'm actually interested in, and I'm going to show you why this enriching of the shape may be of a practical interest. So I'm going to switch to the APL session. So and I'm going to walk you quickly through the following problem. So look, I have an array A, right? So this an array is shape 2 by 6, right? So it's a two-dimensional array. It has 2 rows, 6 elements in each row. And what I want to do, so I want to apply a function. So I have a function sum. Basically, sums all the elements in the array, and I want to apply a function sum to the tiles of the array A. So I want to tile the array A into 2 by 2 pieces, right? And apply sum to each piece, and basically get back 3 elements. So when I say tiling, so I mean 0, 1, 6, 7, 2, 3, 8, 9, and so forth. Now, the point is that currently there is no single operator that's doing this. I mean, you can surely write a small expression that's going to compute this, but not with a single operator. So, but let me tell the other part of the story. So, okay, let's assume that we could have tiled this. Then we would end up with an array of a shape 1, 3, 2, 2. Oops. That would look something like this. So you see, if I plainly reshape the array A, it does the tiling incorrectly, because it tiles the array from the flattening, and we need to tile it a bit in a smarter way. But okay, what this tiling is good for? This tiling is good for because there's a very frequent operator in APL that is called the ranked operator. Looks like this, and what it does, it allows me to say, okay, I have my function, and then I can pass an argument to the ranked operator and apply it to well, let me do it like this. So I can pass an argument, and I can apply it to this array. Okay. So what it just said is that, look, I pass the argument 2 here, and it says that it is going to apply a function to the elements that you find in the last 2 dimensions, right? So in a way, it's something like a generalized map. But if you're dealing with lists of vectors, then, well, I mean, you can only map in a certain, well, in one way, because your element type is fixed and you don't have any dimensions there. But if you're dealing with homogeneously nested vector, then in principle you can decide, and your operation is rank polymorphic, so sum is a rank polymorphic, so I can apply sum. Oops, I can apply sum to, I don't know, 5, right? So it works perfectly fine. Then I can decide which elements I'm going to feed to my function, right? And in that case, and in this case, what it does, it actually, this ranked operator says, okay, I can cut my shape vector into the outer part and inner part, and apply, well, and map my function on the outer part, right? Okay, but coming back to this hierarchy. So why is it useful? And I think the core, the important answer here is this. The arrays, in principle, yes, they are views of a sequence. But why would you ever want to create a view if a sequence is kind of works fine? And I think the answer here is that you want to create a view because you want to attach a certain proximity matrix to your elements, right? In a sequence, each element has only up to 2 neighbors, right? In the multidimensional array, the number of neighbors go up, and you can talk about much more interesting distance relations between the elements. The same thing happens here. So look, if we want to preserve the operations via reshaping, we'd reshape it like this, and then we're almost there, and then we'd need to map over these dimensions, right? But these dimensions are spread; they're not neighbors. So there's no way to apply this ranked operator. However, if we would assume that our shape were a bit richer than just a vector, then we could consider the shape like this, right? And in that case, we can do something with this operator. For example, we can take a column, we can rotate the matrix, right? So we can bring all the operators that we use on normal arrays in the position of the shape, and remap one shape into another in such a way that the effect on the array elements can be trivially computed. So if you can map one shape into another, you can always reshuffle the elements of the array accordingly, right? And that's exactly what I'm doing in the paper. So I have an Agda formalization. I don't have time to go into the details, but please have a look, where I extend this idea of the ranked operator and make it level polymorphic. So what I'm saying is that, well, it doesn't really matter how rich your shape is. All you have to do is you have to define a way. So you have to define me a hyperplane that cuts the shape into two parts, right? And if you do it, and if it's actually a hyperplane, then these two parts can be turned into, well, then the array of the shape that is cut into two parts can be turned into a nested array, and then you can do the map on the outer level and feed the inner array tiles into the function, right? So I describe this idea very precisely in Agda, and I show how it's done. But the overall intuition behind this is exactly that, right? So by putting richer structure into array shapes, we can use all the huge amounts of operations that we have already on the arrays. Okay. And okay, I'm going to skip this. I'm going to just go to the conclusions. So what happened here? So I tried to use containers to formulate this multidimensional arrays, and I discovered an interesting operation. And I think there's still plenty of things to study about this operation. And I discovered this interesting hierarchy that seemingly that is very natural at two levels, because, for example, in APL everything is an array, right? And therefore it is nice that this hierarchy mimics exactly that. So you can do all the operations that you do on shapes and on scalars as you can do on arrays. So I formalized this in Agda. There were a few problems that I described in the paper. I've implemented key array operations, reshaped, flattened, ranked, and so forth. And I worked out the example. So the ranked, this ranked operation is the hardest one. It's all available at GitHub. And I'd like to say big thanks to Peter Hancock, who should have been an author of this paper, but he preferred to, play harmonica or something instead of paper writing. And Boris Schultz, who we spent a productive few days on discussing this multi-dimensional arrays and bending our minds over it. Yeah, I think that's it.
Okay, thank you, Artem. Clap, clap, clap. Okay, so we're a little over, so I think we only have time for maybe one question, but this was asked by both Manuel Barons and Wouter Serstra, and the chat was essentially, do you have an explanation for how to understand this diamond operator as an operation on the functors induced by the containers, like directly working in the semantics?
I'll have to think about this. So I think the explanation that I provided works the best for me, because it captures a lot of intuition. But for functors, as I said, it is operation with weird properties. So I'm not sure that if there is an explanation, that it's not a trivial one. So there's something funky happening there. Understanding it via this tensor product seemingly is the easiest way, but I might be wrong.